So, welcome back to the part 3 of this series of CFD. So, now we'll be jumping on to the next step, that is mesh. So, as I said, meshing is one of the most important um, part of CFD. I'll just zoom out a bit. Okay. So, yeah, mesh, meshing. So, yeah, what is meshing? So, in simple terms, meshing is the process of dividing your geometry into smaller cells, into smaller cells, right? So as I was talking about before, let's say the fluid flow example, where we were dividing it into multiple control volumes, right, or cells. So this process is called meshing. Okay, if that makes sense, correct? So you have divided into small meshes. So now under each mesh or the control volumes, you enforce conservational equations and then solve, and that is your CFD, right? So meshing, as I said, exactly is why is it it is the it's one of the most important methods, because unless you mesh you cannot enforce any laws, you can't enforce any equations on the whole body. You have to divide into mesh, right? And why the is it necessary that you have to divide into mesh? It's all about accuracy. If you just keep it as a whole body, you can't um, apply equation for one whole system. One whole system, it's just impractical, because it will give you the most absurd answer. uh, because again, parameters, the values of phi keeps changing with the distance. Let's say, again, it depends on parameters, but if it does, then taking one whole system doesn't make sense, right? That's, you have to divide into meshes, and that is what uh, meshing does. So you divide into smaller control volumes, or control I mean cells, and then you enforce uh, your equations. Now, so that's a very simple definition of mesh. Now I'll just jump into the types of mesh. Types of mesh. So in types of meshing, you have, again, forgive me for the handwriting. I'm using a tablet pen, which I'm not much used to, but yeah, I'm trying my best. So you have quad. This is just your normal square shaped. Then you have your triangle. Then you have hexahedron. Hexahedron is, if you hexa, okay, my bad. Hexahedron. So this is more like a cube, just a complex term for cube. Right? And then you have your tetrahedron. Tetrahedron. Correct? So now tetrahedron is, just take 3 points over here and join them. So this is your tetrahedron. So these are your basic mesh types that you have. Then of course you can have more complex ones like prism and polyhedral. Polyhedral. So in polyhedral, it just depends on more size. So again, it depends on your geometry, on what type of mesh you have to go through. So these are like just the names and the shapes of meshes that's available. Uh, Now the a more informative categorization of mesh or differentiation would be your differentiation or categorization into two types. That is your structured mesh, and your unstructured mesh. So in your structured mesh, I'll just check if there's a better. So in your structured mesh, so it's just easy to understand. So if they follow a predictable pattern, so I'll just write it, predictable pattern. It's like a textbook definition that they say that if you have a predictable pattern, or they have like a regular neighbor, then it is your structured mesh. So how I would explain it, or how I understand it, is that if, let's say, your I have suppose a square mesh, if the orientation of the neighboring cells are same of that as the central one, then you have a structured mesh. Okay, now what does that mean? I have taken this as my central mesh. If the neighboring meshes have the same configuration, that is their configuration or the orientation, that means they're straight, just like this. So all of them, if I just shift to this, if I take central, then again the rest of the configuration remains the same. Then that is your structured mesh, right? So your orientation of neighbors, neighbors by here I mean is the neighboring cells, neighbors are same of as that of the central slash the, I don't know, chosen element, mesh element, right? Now going to unstructured mesh. So okay, I'll just give an example over here. So for example, your normal square, as I told here, or your hexahedral. So technically, if I just extend this 2D mesh into 3D, you will get hexahedral, right? Oh my god. Yes. It's kind of tough to write with this, but yeah, bear with it. So hexahedral. So these two, that is your quad. So quad and hexahedral. These two mesh types come under your structured. So these are examples. I mean, you'll have a ton of others as well, but these are the basic regular ones that you use. Unstructured mesh, so totally opposite of what I talked about. So it's just random configuration or orientation. That is now the simple. If I have this a triangle, now the neighboring is something like this, then like this, then like this, then like this, 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 right? So here, I guess I'll just make it a bit better. Excuse me for that. Yeah. So let's keep it straight. So as you may have meshes like this, right? So this is my normal triangular mesh. Now I'm selecting this mesh, right? Let's call it M1. So now this mesh, this, it doesn't have the same configuration as this. Now, okay, the upper two and these neighbors, I'll just denote it with red. So these ones have the same configuration and no doubt about it. But then the others, so I'll take blue. So these meshes, these are of opposite orientation, right? That is, they're like 180-degree different from the mesh element that I've chosen, right? So this case is what we call it as unstructured. That is, even if there's one mesh element that is of different orientation as the mesh element that you have chosen, then that is called your unstructured mesh. And here the examples, just one, I just took it right now. Near triangular, then if I extend triangular to 3D, you have your prism, etc. Okay, tetrahedral, tetrahedral in core if you use, then prism, triangular, etc. These all are unstructured mesh. Okay, so just to give a gist again, structured meshes are those where you have such that your orientation of the neighboring elements is same as that of your mesh element that you have chosen. So it's the same configuration as the element that you have chosen. This is a square, this is 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 square. All of them are, uh, I can say the axes are parallel for all of them, right? And this, if you see, the triangular one. So here you have this triangle if I've chosen. Here it is of opposite orientation. Here also it's opposite, here also it's opposite. Even though these are same, but since there are opposite uh, orientational differences between these two meshes, you call them directly an unstructured mesh. Okay. So now why does it matter if you have um, what do you call structured or unstructured mesh? Well, it's simple. So structured mesh is just very accurate and fast. So it's accurate and fast. But when you have complex geometries, there are times when your structured ones fail. So structured might fail. By fail, I mean that it might not cover the entire uh, element, right? So if I have, suppose, a shape, I don't know, like this. If I can't have a structured mesh. If I have, if I make a quad, right? If I make like square, just imagine I put a graph paper on the top and I make square like meshes. You can see that the edges here just cannot be covered using a structured mesh. The orientation will be different. So yes, that is why you have unstructured mesh. So this is used for complex geometries. So hopefully you have understood the difference between these two types of meshes. So now there's another type. So that is just technically, I it's just a mix of both. So I'll just call it, what we call it is the third type is hybrid. So nothing much to understand. So you use structured plus unstructured meshes, right? So this is again when your geometry gets um, complex, or when your like edges are kind of weird, then you use your hybrid, right? So for the core, if like this, something like this, so what I can just make a square here. So I can do this as structured, suppose a quad, and then here I'll go with unstructured on the outside. So this is your hybrid mesh. So these are the three types of meshes that are important to understand, and hopefully all of you have understood what it means. So now we'll just touch on two other smaller types. So now we'll just jump onto the remaining ones. So okay, pen please. Yeah. So that is your O grid. So these are stuff that you might not find in conventional videos or textbooks, but we'll just cover it because these are more like optimized meshes and they are not like any conventional mesh type. So what is an O-grid? So it's like you can say it's like a mesh technique that is characterized by I don't know, lines or mesh lines that, imagine like you're wrapping around a curved geometry. So when you wrap around something using those mesh lines, you can get something like an O shape, right? So mm, assume I have some shape like this. Okay. Um, I mean, yeah, suppose I have uh, airfoil. Okay, it doesn't look like this exactly, but yeah, and I suppose cut it from here, right? And I have to mesh this. So now imagine that you're putting a graph paper, right? So I have a graph paper. Now when I put it on this surface, so how will you see it? You'll see it like this, right? And then if I fold the rest over pieces, right, that is towards backside, you will find something like, you'll find the edges to be crumbed up like this, right? It's not going to be a perfect line or something. You'll get, like, if these are the edges, the edge of the circle, you'll find edges like this, like jumping over, or like just weirdly shaped, right? So this is what you call an O grid mesh. So when you, like, just for an example, as I said, just remember it as, if I am taking something circular, something like this, I'm taking a graph sheet, putting it over, and then the remaining parts, I'm just folding it above the edges. So the edges look kind of distorted. So that type of mesh, right, for the curved surface is what you called an O grid mesh. Okay, so if I have to just define it like a technique uh, characterized characterized by mesh lines that wrap around a curved geometry, a curved geometry, right? So this is your O grid. So hopefully you have understood O grid. Then you have another, that is C grid. So this is the only type of things you have to know. So C grid. So C grid. So C grid again. So this is used for wake resolution, and if you have like blunt leading edges. So now I have, suppose, a cylinder. It's an easy example. Again, take a bigger graph sheet, and so you take a big graph sheet, right, and you put it onto it. So let's say the graph sheet comes till here, and then you just wrapped around, and here again you fold it around, and here you have the sheet, right? So it's more like an extended O grid, right? So why the name C? So if I had a cylinder, if I took a graph paper, so my paper would be technically folded like this, right? And whatever mesh comes on this is what we call the C grid. So hope you understood that, right? So this is mostly used for wake resolutions, and blunt leading edges, blunt leading edges, edges. Okay. So this is your C grid, just an extension to O grid, and then you have your H grid. H grid is nothing like, just more like a ladder shaped, like just your simple rectangular topology, just something like this. Your normal mesh, right? That is your H grid. So it's specific. It's like just a specific type that you talk about. Mostly used in like channels, right? So this all comes useful when you're going into, so under um, what you call um, in under ANSYS Fluent, you have an option called, you might have seen, virtual topology, right? So here where you create a virtual object, like it doesn't exist, but you put it so that it can be meshed easily. So these all, then you use these type of meshes for easier meshing. Okay, that is OC and H grid. I mean, you even use it without virtual topology, but you do see it in such cases. So when you have, as I've given example, like um, as I said, for airfoil or anything like that, if you can use an O grid. Then if you have, if you are resolving a wake, or if you have leading edges or like a cylindrical pipe, then you can use a C grid, and then H grids are like used for channels. So yeah, that is all about your meshing types. Now I'll just go to one of the most important parts of meshing, and that is your boundary layer. That is boundary thickness. I'll just increase the thickness. 5, yeah. So, oh sorry, yeah, boundary layer meshing. So why is boundary layer meshing very important? So what does this mean? So let's assume I have a nozzle, right? So this is my throat, this is my chamber, this is my nozzle. I mean the out. This is my outlet, right? So this part is what you call a nozzle, right? So you have the inlet, you have the you have the chamber from which you get the air or the propellants or the mixture, and then the gases expand and this get out through the outlet. Okay, so I don't know what I've written, but yeah, this means outlet. Okay, scratched out outlet. But yeah, so now here, why do we need a boundary layer meshing? So one of the most important regions in a geometry is your boundary, because your boundary is meant to have interaction, right? So wherever there's interaction, you need to be very fine in order to capture those interactions. So let me say this is my boundary. Okay. So my boundary layer here. So I need to have, so the meshing needs to be very perfect in these boundary layers so that I can capture the interaction between the walls and the air flowing, right? So the air acts, or the air or the propellant or the mixture of gases that expand, they all act different at the walls, in the sense that your walls can have friction. Again, in Fluent, when you do like a normal simulation, you usually take no slip condition. No slip condition, that means no friction. But of course, that is not the case in practical reality. You will have friction. So let it be friction, or um, when there is boundary layer separation. Okay, so what is the boundary layer separation? Assume, so the gases are normally traveling like this, right? So when you're at the boundary, your velocity of air is not the same as the velocity of air that is flowing to the middle, right? So you have like more like a gradient here. So this whole thing is your boundary layer. So it causes a separation of flow. So this lag in the velocities cause the separation, right? So that's called your boundary layer separation. I mean, you can just relate this to your Newtonian physics. So where you have, suppose, I don't know, a liquid, and because of different viscosities, you have seen that, I don't know, the velocity goes, there's a gradient, and then you used to check the area, and then you would calculate the viscous force. Okay, yeah, correct. So that is exactly how uh, you can imagine boundary layer separation to be. So as I said, so that's why your boundary layer is a very important region in any geometry, and it is not necessary that it has to be like a geometrical boundary, right? Anywhere where there's separation happening. So if I have an airfoil, I mean, just example, not necessary. Um, if I'm having my flow is getting separated here, right? Or there's also probably a chance that you have different like different mediums. So wherever the behavior of the fluid changes drastically, or where there's a separation in flow, right? That is, there's a separation in flow. that is when you can call it like a boundary layer. So this is where your mesh has to be most refined or resolved. Why? Because it has to capture all the behavioral changes that's happening. Correct? So hopefully you understand why this is a very important uh, scene or topic under meshing. So uh, in order to capture this huge gradient that I talked about, we need tinier cells. That is a more fine refinement of mesh, right? So there's something that we call as inflation. So inflation layer. So you have pretty sure heard about this if you know CFD or if you have opened Fluent. You can see inflation layer under meshing. So what are inflation layers? It's just simply a prismatic layer near the wall. What does it mean? If I take a thick, if I like just take a graph paper, okay, with some mesh, I mean the boxes are the mesh. Now it can be fine, very fine, depending on it's just depending on how fine you want. So it depends on the user, depends on user. Let's say so if I so of course you are supposed to have it like very fine. Um, suppose I have very fine mesh, and this is like a graph paper assume. So it's like a layer, and it has some thickness, right? So thickness, it has some thickness, and that is what I'm going to put over the boundary. So let's take like an airf. I can never draw an airfoil properly in this pen. But yeah, I mean, hopefully you're getting the point. Oh my god. But yeah. Okay, whatever. So I mean, this is not exactly how an airfoil looks, but yeah, this assume this is one. So now you put this thick layer on top, right? By thick, I don't mean it's very thick. Of course, it's not. It's again something that you can define. So it's you have some thickness of this layer. Now the thickness of this layer. So like assume you have the. I'll just take it in a different view. So this is the um, I don't know. Yeah, this is suppose the surface you have to mesh, and you have put the graph paper on top of it. I'm just telling graph paper, but just in reality, it's the inflation layer. Okay, so you have put the inflation layer on top, and this has some thickness, and this is the top view, and from side view it looks like this, right? So this thickness, some thickness T, is what we call it as boundary layer, or the first boundary layer height. First boundary layer height, or the first layer height in short, right? So the first layer height or the first boundary layer height is the distance, you can say, between uh, your this the wall to the center of the uh, inflation layer, right? So I hope it's understood. So if this is my oh my god, why can't I erase that? Start using shapes. Yep. Yeah, perfect. So now if my surface is like this, suppose, right, and this is my first inflation layer. I'm sorry, this is not boundary, this is inflation layer. My bad. Inflation layer. Inflation layer. So the distance from here, that is the center, right? If I just assume this to be the central axis, then the height from the center to this surface, right, is my first layer height. layer height, right? So this is my first layer height, and then next term is your growth rate. So here suppose I have a thickness T, right? Then the next layer, it's not necessary it has the same thickness, that is T. So it might have 1.2 T, right? That is 1.2 times the thickness of the first layer. And similarly, this keeps increasing. That is 1.2 times, and I'll just call this T2. That is T2 is 1.2 times T. So the T3, the thickness of third one, is equals to 1.2 times thickness of third. Sorry, thickness of twice. So that's how it keeps growing, right? So here you can see that the rate at which the thickness is growing is your growth rate. Growth rate. Fine. So this I can define that rate at which the thickness of the layer, boundary layer, is increasing. So this is usually typical is around 1.1 to 1.2. You don't drastically change the growth rate, of course, because you have to capture every refinement. I mean, you have to capture every detail. The number of layers, another parameter. Number of layers is total number of inflation layers. I know, again, typically you have 10 to 30 of these. I'm just telling typically, so it depends on problem or the surface or the geometry. But here, most of the time for a problem, it's your 10 to 30 number of layers that you're taking. Now, the most important parameter, that is probably one of the most confused one as well, is your y plus. So what is y plus? So it measures the distance of the so it measures the distance of the layer from the wall, but in turbulent units. Okay, so what does it mean? Well, it's simple. I'll just draw shapes and explain, because again my drawing in this with this pen is horrible. So yeah, so I have this, then I have this. I'll just keep a different color for each layer. Oh my god. I'll keep this as blue, and then this, I'll just keep this as the last layer. Okay, this kind of rage bait, but bear with me. Oh my god. Okay, a slimmer one, and I'll put it yellow color. Okay, right? Okay, this is kind of makes sense. Now this is suppose my surface, right? Of course it's touching the yellow one. So this is my surface. Now you know what, I'll just rub out this. Just rub out the line. I'll let it draw one line, so it makes things better. Okay, I'll just assume the line to be the surface. So yes. Okay. So yeah. So let this be the line or the surface. Now the distance from the center point of the yellow. So I'll just call the first layer as 1, 2, and the third one as 3. So the height from here, that is, I'll call it as y, right? That is the distance. So y is the distance from wall to center of the layer. Okay, so this is my y. But now if I convert this into turbulent units, okay, into turbulent units, this is what is my y plus. Now how will I convert to y plus? So if you know the Reynolds number, right? How would you define Reynolds number? Reynolds number is your rho v L by nu, right? It's rho v L or rho v d, depends. So instead of L here, I'm just going to replace with the y. That's the difference. I mean that's the distance. So I'll just do rho v y divided by nu. That's your kinematic viscosity, and that everybody gives your y plus. Understood? So your y plus is technically your distance from the surface to, okay, I'll just take an example, another. So from the surface to the midpoint of the boundary layer, sorry, the inflation layer. So this is y, but when I convert the y into, when I replace it in this equation, rho vy divided by nu, I get my y plus value, right? So this is my uh, this is the definition of y plus, right? So y plus is your distance from wall to the center of the layer, the inflation layer, but in turbulent units. And why this is very important? Because this gives you the uh, an idea of how fine or how resolved your mesh is at that layer. So if I have my y plus less than 1, what does it mean? It means that your y is, okay, so your y is directly proportional to your y plus, right? So your y here, again, since nu and v would change at each layer, right? Again, your velocity at here, here, and here are not the same. That's exactly why a boundary layer is a separate, or it's a distinct condition, right? So it's not that these always remain the same and you just keep substituting y. Nope, it's your y, v and nu keeps changing. So based on that, you get the y plus values, right? So when y plus is less than 1, what does it indicate? It indicates that, okay, I'll just go down. So when y plus is less than 1, it indicates it's fine mesh near boundary. And when it's less, I mean it's like y plus is around, let's say 10 or 30 to 300, then it means you have lesser fine, or you can call it medium or mid or coarse mesh, right? So my y plus determines how fine the mesh is, and that's why y plus is one of the most important terms in meshing, right? So hopefully that is understood. And so where can you see this y plus term? So when I'll be talking about turbulent units, sorry, not turbulent units, turbulent models. So you can see models like uh, k omega SST or k omega standard or k epsilon. Okay, so what are these? These are turbulent models. So these are models that uh, try to find out the turbulent viscosity, so through which you find the turbulent momentum. So these models use different methods to find it. So technically, in short, if I tell, so your k epsilon is excellent at your central flow regime, and it's very weak at the boundaries. So here, what can you expect? Since I told it's weak at the boundaries, so you can say that your y plus is from around 30, so your y 30 y plus 300. That means your y plus lies between 30 to 300. It's not that fine. Exactly why it's not able to resolve much under the boundaries. So that's why your k epsilon performs very poor at your boundaries. Then you have k omega standard. So what does k omega does? What does k omega do? So if you have a boundary layer, you have flow here and you have flow here. So k omega resolves this part accurately, very high. So it's now if I say for this, you can guess it yourself. So y plus is very fine. Yeah, the mesh near the boundary is very fine. That's why the model is able to resolve the boundary accurately. So your y plus is less than 1. So these are conditions for each model that you will see as you go forward. But yeah, now you can see why or how important y plus is to us, right? And k omega SST is just a mix of k omega standard and epsilon. So you can have both these conditions. But usually this is the most, more preferable ones for conditions or situations where you need the boundaries to be highly resolved, right? And it's always more um, it's better to have the boundaries resolved. Again, you might have conditions where you don't need to focus much on boundaries because that is not much important to you. There are conditions. I'm not telling that every time you need to have y plus less than 1. So of course that, or else you wouldn't be needing k epsilon, right? You can just directly go with this k omega. But yeah, this is why y plus is such an important parameter. So yeah, that is about the parameters. I'll just recollect it to you again. So let me move this to the side. So you have your boundary. Why do I keep saying boundary? My bad. Your inflation layer. Okay, so this is your inflation layer. The parameters is you have your first layer height, first layer height, then you have your growth rate, you have your um, number of layers, you have thickness, layer thickness, and finally the most important, the dad of all, y plus, right? Hopefully you have understood what each of them means. If not, you can just rewind and watch it again. So yeah, now just a little more left in meshes. Okay, so now we move on to mesh quality matrices. So okay, mesh quality metrics. So this is again very important. So let's take, go on with each of the metrics. So number one is your skewness. So skewness measures how distorted, how why is the pen acting so weird, man? How distorted your mesh element is, right? So a perfect mesh would be with skewness equals to 0. So again, what is the question I asked? How distorted my mesh element is, right? So if my mesh element is 0, skewness is 0, it means it's least distorted. So this is perfect mesh, and if skewness is equals to 1, it means it's worst, is the worst mesh. You, of course, you shouldn't go for a mesh with skewness equals to 1 because it means it's highly distorted. So I'll just tell you general metrics. So if it is less than 0.5, it's good. If it is greater than 0.95, it's bad. And if it is less than 0.85, you can take it as acceptable, right? So less than 0.5 it's good, more than 0.95 it's bad, less than 0.85 it's acceptable. Oh, just remember this. just keep have an idea that if you can't remember this, it's fine. Just keep have an idea that skewness 0 means it's more distorted. Oh, sorry, it's less distorted. So 0 means it's not at all distorted, so it's a perfect mesh. 1 means it's more distorted, it's the most distorted, so it's the worst. So if you remember skewness with this question, that is how distorted your mesh element is, you are good to go. Okay, so coming to the second um, quality second type or second matrix, it's your orthogonal mesh quality. So what this does is technically measures the uh, angle or the alignment between the line that joins the two centers of the mesh element and the face, I mean the line that passes through the face of the mesh element. Okay, so I'll just take an example. Suppose I have a mesh, hexahedral mesh, right? And this continues. Okay, so here the mesh element has the centers, and this is the line, and it faces, I mean the face of the element is like this, I can say, right? So it means it's orthogonal. Now if I have the mesh, suppose like this. Okay, my pen is lagging, my bad. So yeah, if I have something like this and the other one as well connected like okay, I'll just rub it. So I'll just take this pen. So assume I have a element like this. Draw it perfectly this time. Right. So here my center is still the same, but this is on, let's say, an alignment of 45 degree. I mean, it's just assume it's tilted like this. The meshes are tilted like this, right? And here or here it is like this. It's just one side, and your faces face up. Here your faces are facing at 45 degrees. So this is the line that is connecting the centers are still the same. Let's center to center, same as this, but here the it's facing outward at 45 degree. So this is an orthogonal, you have an orthogonal difference, and this is exactly what you call and what you measure for orthogonal mesh quality. So if it is perfectly aligned, you'll have a value of 1. So it means perfectly aligned. And this is an example of an orthogonality 1 mesh, and you will have it as 0 if it is the worst aligned, right? So again, for normal metrics, above 0.2 is minimum. So if you get less than 0.2, you just you go with a better mesh, and if it is greater than 0.7, it is a good mesh. It's orthogonally it's good. So yeah, so hopefully you understood these two. Then you have another mesh metric, but this is common everywhere, so you have pretty sure heard about aspect ratio. So aspect ratio is technically your longest side of the mesh, longest side divided by shortest side, right? Yeah, so this is your aspect ratio. And now aspect ratio, it just depends on the geometry, but usually for boundary layers, you keep the aspect ratio at around 100 plus, and for if it is not a boundary layer, else you keep it low, right? So this means, what does this mean? This means it's more expanded, right? So you can have more fine refinement. So that's why at boundary layers you keep it as 100 plus. And yes, so that is about the metrics of meshing or mesh quality. So you have skewness that measures distortion, you have orthogonal quality that measures alignment. So in skewness, if perfect is 0, that is 0 distortion, and worst is 1, that means full distortion. Orthogonal quality is different, it's totally opposite of skewness, that is it measures alignment. So your 1 is perfect and your worst is 0, right? So going to aspect ratio, it is longest side by shortest side. For boundary layer you keep it more than 100, and elsewhere you keep it low, and just to have a better resolve or having more finer at the boundary layer, right? So now talking about adaptive mesh refinement, another topic, the last topic that we are going to cover in meshing. So adaptive mesh refinement. So it's simple. Um, so the solver automatically refines mesh when needed. Okay, so for example, suppose a shock wave was detected. Okay, so initially before the mesh was something like this. Okay, this is just an example with plus minus minus, minus saying the gaps. So this was a coarse mesh. Then after it detected a shock wave, it becomes plus 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 plus, in the sense that the meshes have been more fine in order to capture more details about the shock. So technically, when your solver automatically refines mesh in order to adapt to the behavior of the fluid, or it spots a condition such that it accounts for a better mesh in order to capture those details, that is your adaptive mesh refinement. So hopefully everything in this video was understood. Uh, if not, you can just leave a comment in order to, and I'll help you out in the comment. But yeah, so technically that is everything about mesh that is important to be understood. And there's a lot of stuffs in meshing, but these are the stuff that are important for you to know on a general basis. If you're starting with CFD and you want to know deeper, you want to have a deeper knowledge in CFD, then yeah, this is a good start. So yes, now the next topic will be your solvers. So okay, solvers will come later. First we'll have numerical discretization. So since now you have meshed, you now discretize equations. So we'll talk about this in the next video, and yeah, thank you for watching. Bye.